another warm welcome to everyone here
Differential
for AP
equation.
Calculus BC Live. And as you can see, we are continuing our week-long series connecting AB to BC with today's specific topic, Fundamental Theorem of Calculus. And as with all of our videos, we encourage you to download the associated materials. They can be found in the description below the video as a direct link to our Dropbox. And you've probably noticed here lately we have a sort of a mixture of our problems. We have these quick checks at the beginning that are sort of standalone, isolated problems that focus on the topic of the day, and then we segue into a pair, or in some cases, some days we have maybe 3 or 4 free response questions where we can then sort of weave or integrate, no pun intended there, the topic of the day into future AB topics and into topics, in this case, into the BC realm. And boy, do we have a couple of really great FRQs today, some very long FRQs. We almost ran out of letters of the alphabet to break those FRQs into certain parts. So a lot of great content that you're going to see in that regard. We also have great news to share. We'll probably share that at the end of the show, but we will be doing a few more episodes at the very end of the month of April, and we'll talk about those where we're going to be able to help the kids get a little bit more acclimated to this new form of this AP exam of this year. And so stick around for that. And we also have our dogs of the day as well. My name is Tony Record. I am joined by my esteemed colleague and good friend, Brian Basswater. And Brian, I tell you, I just think this keeps getting better and better. I keep like thinking I'm in some dream here, and I'm so fortunate to have this opportunity to work with students, to work with you. So it's just been great.
Yeah, it's been amazing. And Tony, I always mess this up because I always look the wrong way. I need to go back and watch these on YouTube because you're always looking the right way, and I think I always end up looking the wrong way, trying to figure out where you are. And so I think Tony is like the tech savvy guy. We always talk about Tony being the tech master, and Brian is the guy that doesn't know what's going on half the time. But I think I'm looking at you right now, right? Can you see me?
I think so. I see you,
Okay,
Brian.
cool. All
High
right.
five.
Yeah, I mean, we're definitely pinching ourselves because Tony and I, we've done a lot of work for the College Board, but I remember, when I first started teaching 10, 15 years ago, I loved College Board. I wanted to be a part of it. I loved the AP curriculum, and I would see names out there of AP calculus teachers that I wanted to emulate, that I admired, and there's still people out there. Like I remember when I first started teaching, you were teaching before I was, and I knew who you were and wanted to be like you and some other teachers. And then I remember this was a story I'm going to tell us real quick, but I've been reminiscing a little bit because I know a lot of our students here are seniors, and so they're missing out a lot of those great senior traditions. And at my school, we would have kind of some senior pranks, right? And they were always good natured and nothing bad. And I won't go into detail about what they were, but there was one that it wasn't so much a senior prank initially, but it became one at my expense. And so when I first started teaching calculus, I enjoyed the College Board. I didn't know how it worked, but we were doing one of these FRQs, right? And the students have seen a lot of the FRQs, these free response problems that I'm writing each day. And sometimes you get these FRQs that are just really, really cool, right? These College Board problems that are really unique, and you're like, wow, what a neat question. I think teachers more often say, what a neat question. Tony, when you tell your kids, oh, this is a really cool question, does that on their end mean they're going to hate this question? Like if we love it, they're like, that's not a good sign, right? It's going to be really hard or different and kind of confusing at first for them. But the College Board comes up with these really cool questions. And in one year, there's a problem that was just beautiful. I thought it was amazing. It was my first year teaching Calc BC. And it was so amazing. In fact, in the moment we did it, I was like, guys, we have to stand up and give College Board a round of applause. So we stood up in class, we lit, standing ovation. I'm not exaggerating. And I was so moved by the problem. I actually wrote College Board a letter, just thanking them, like how beautiful the problem was. I wrote a letter. I think I went online and looked like College Board's address. I don't know who it went, just to the College Board, like Dear Santa Claus. Sent it to them. I was pretty ignorant about how the whole thing worked. Well, about 2 weeks, 3 weeks later, I got a letter back sent to me. It was sent to my school, and it was sent to me from the College Board, and it said, thank you for your letter. We appreciated it. Normally, we only get complaints about our problems, and it's so nice to have someone appreciate and our effort and appreciate what we did, and we really enjoy that. Thank you so much. And I was so proud of the letter. I actually had it framed. I framed not just the letter, but I framed the envelope that came with it. I made a frame for it, not exaggerating, and I hung it up in my classroom. And for like the next, probably 3 or 4 months of school, I would brag about that letter and that thing all the time. It became this running joke in class that every day I would, brag about my letter from College Board, how that made me important and how cool I was. And the last week of school, again, I was bragging about it. And my student said, Mr. Passwater, we wrote that letter. And I was like, no, you didn't write that letter. You guys are playing a prank on me. You're trying to make me think you didn't. And they had their laptop with them. They turned their laptop around and they showed me whatever the program, the Photoshop they had done. And they wrote the letter. And I want to tell you, I couldn't tell if I was impressed or devastated more, because they went and found a letterhead that looked like College Board. They found all the College Board names and put it on them in the margins with their titles. They had another teacher sign it. They had a real, like the person who it was a College Board employee in case they looked it up. They had a teacher kind of fake the signature. And then on the envelope, they even printed a fake postmark stamp on it. They put a stamp on it and they had it fake postmarked, so as if it had gone through the mail, and they snuck it in my school mailbox. I would think it came directly mailed to my school. It was a pretty elaborate prank, and I was kind of half devastated, but I kept it hanging up, And so I still have the letter, still have it, but it kind of made me miss the senior pranks, and it kind of made me miss some of the things. So I definitely feel for our seniors who are out there today that are kind of missing some of that. But we're looking forward to a great lesson today, and I'm looking forward to jumping right into it and doing some really cool problems involving the fundamental theorem today.
All right, well, let's go ahead and get us started. And as you already have seen, the fundamental theorem is our big focus of the day. And if you want to think, what does the fundamental theorem of calculus really say? Well, it says a lot of things, but I guess the first thing that we want our students to really grasp from that is it's associated with the area under the curve. So as you can see in the picture, we just decided to call this curve f prime of x. It could be anything, f of x, g of x. We're going to do a lot of manipulations with area under f prime today. And so if we were to integrate that f prime from a to b, that's going to depict that area under the curve. And we call that the fundamental theorem of calculus. But there's just so many different ways that we can find that area. It doesn't always have to be some integration technique, some manipulative uh, type of procedure that's used in an analytic environment. It can certainly be used in a geometric environment and a conceptual environment. And those are the things that we're going to try to expose you to today. So that's what we want you to think about. Fundamental theorem of calculus associated with finding the area under the curve. And so we've got today's big idea, fundamental theorem, but we also have these subtopics that we're going to weave in, like area approximations and finding these exact areas and connecting things in the accumulation. And so our topic on the left side kind of begets our approach on the right side. Area approximations, yeah, why not? Riemann sums, trapezoid approximations, the way that we've been talking about these for the past couple of weeks. Now, finding exact areas, that's where we're going to spend a lot of our time today, because there are really a lot of different ways to do that. Three that we're going to focus on, with whether it's geometric procedures, whether it's using straight up the FTC, or possibly properties of integration. And then we can connect integrals and derivatives with the fundamental theorem. And of course, the idea of accumulation, which sometimes we kind of associate that with this fundamental theorem of calculus part 2, right? And we're going to focus on a few of those problems a little bit. We call that the modified fundamental theorem. So as we said before, we're going to go ahead and dive into some quick checks, which are some isolated problems here that have maybe one, maybe two parts that will feature these subtopics. And our first subtopic is Riemann sums and area approximations. So from this particular problem, it reads that we're going to let f be a function that is twice differentiable for all real numbers. The table above gives selected values for f prime in the closed interval 2 to 12. Our job is to use a right Riemann sum with the four subintervals indicated by the table, by the data in the table, to approximate the definite integral of f prime of x from 2 to 12. Show the work that leads to your answer, which is always important. So if we decide to label what we're doing, this is great communication, by the way. It's something that certainly wouldn't be necessary, but if a student were to identify what they're about to do, we're about to approximate this definite integral, that would be great. We would certainly prefer that the student put an approximately symbol after that, because we are using a Riemann sum approximation. So that's one thing that you want to consider. So there are times that we could look the other way, and if they put an equal sign there, it's not such an egregious mistake that we would penalize the student, but you certainly would want to at least instill this into your students. And students, you want to also know that you are doing an approximation. Now, the right side of this symbol is what the most important piece is. So what we have to do is know that we're talking about four subintervals here. And as you can see from the table, the widths of these subintervals vary quite a bit. They're just kind of all over the place. In fact, there are four different values, 2, 4, 1, and 3. So with a Riemann sum approximation, we are using the idea of the rectangular shape. And because it is a right Riemann sum, it seems as if the values of the F prime row that are going to be very important will be these guys. So now we just assemble this in the correct manner. So our first rectangle would have a width of 2 and a height that we could define as F prime of 4. All right, and we'll talk about various ways that you can enter this problem here in a moment. And then we would add to that our next rectangle, which would have a width of 4 and a height that is defined by F prime of 8. And we continue this process with our third rectangle, a width of 1, a height of F prime of 9, and then finally our last rectangle with this width of 3 as indicated by the table and a height of F prime of 12. All right, now at this point, we would have to identify what those values are from the table. We have to extract information from the table. You can't really leave your answer in terms of an F of something or F prime of something if they can be defined by the table. So F prime of 4 we can see is equal to 1, and F prime of 8 is this -2, and we just continue this process for F prime of 9 and F prime of 12. Now, the thing that I wanted to talk about here is you could earn points on the AP exam on any given year, not just 2020, but any given year by having written either of those two statements. That would be your first point for usage of the Riemann sum. The key is that you have to show a sum of products. As you can see, I have sums written throughout this, and I have these products throughout. We must make sure that that is written on our paper, whether it's done via function notation or whether it's done via extracting values. That would be acceptable. And as far as this last line is concerned, that would be enough to earn your full credit because it is a numeric value. It can be simplified. I'm not going to go through the specifics of this, but I believe it's going to be 3. You can check that out on your own later, but that would be the most simplified answer. But keep in mind, you need to make sure that you present the sum of products. Oftentimes, a student could make one little mistake throughout this. Let's say that one of these products may have been misinterpreted, and you might still be able to earn a point for the Riemann sum approximation. We sort of get you that little wiggle room. But you know, I think our goal is to try to be as accurate as possible, and let's make each one of those products accurate. All right, so that takes care of our quick check 1 for Riemann sums. Let's move on to quick check number 2, which is going to focus on the idea of using geometric areas. And I'll do part A on this one. So it says we've got g prime, which is the function given above on this closed interval, -2 to 16. And as you can see, it consists of 4 line segments and that semicircle. So part A asks us to evaluate the definite integral from -2 to 5 of g prime of x. So one of the things that it's easy to do, and I've done this many times when I've worked on documents that use the idea of the fundamental theorem with problems that I haven't seen before. And we have this propensity to take the integral of this g prime immediately and say, oh, it's g of x. And I won't argue with that. But okay, so you've got a g of x. What are you going to do with it? You can't evaluate g at 5 and see any kind of crystal clear answer from the picture. So we have to really understand the environment that we're working in terms of finding this area. And because we have a graph of g prime, what better way to actually evaluate this integral than to use the idea of geometric areas. And fortunately, when you have line segments, when you have semicircles, you've got some good, clean geometry at your hands. And that's what we're doing here. We're just essentially finding the area from -2, which would be all of this triangle here, and this, okay, weird shape here. Well, that's not such a weird shape, I guess, because it does stop right here at the 5. Boy, if we were going to go farther into the past that 5, we would be in for some really interesting situations, which guess what your homework is going to be. When you take a look at B later on, you're going to have to consider that unusual shape. So in this case, we just basically have an area that's in red and an area that's in green, sort of like Christmas here, that we're going to have to go ahead and add. So if we find the area that's in red, we see that that's a nice, well-behaved triangle that has an area of 1/2 base, the base being 5, times the height, which is 3. And then the green area, we have to think of being below the x-axis, so we're going to have to use a negative for that. And we can see that that's got a base of 2 and a height of 2. And so we have 1/2 2 times 2. And that numeric answer would be perfectly acceptable in this particular case. If we do choose to simplify, it's going to be 15/2 minus 2, which I believe would be 15/2 minus 4/2 or 11/2, 5.5, 5.5. Okay, but we definitely encourage you to take a look at B to kind of capture that nuance of this very interesting shape that's going on there. All right, pushing ahead, as you can see, if you've got the document in front of you, there are a lot of problems. So we're just going to kind of focus on the ones that we think set up some of the parts of our free response questions that we're going to do today. And I'm going to switch over here to quick check 3, part B, where now the topic is the fundamental theorem of calculus. Is it part 1? Is it part 2? Textbooks will kind of interchange those ideas. So as a teacher, don't worry about what your particular book does. Just make sure that you teach both parts. The normal, what we say fundamental theorem at the beginning here, where we integrate from A to B, and then you've got that other facet that kind of ties into accumulation. It uses the idea of a function defined as an integral, and we're going to see some of those in a little bit. So for part B, we have this chart. The function g is continuous, has derivatives of all orders for all real values of x, selected values of g, its first and second derivatives, and capital G, the antiderivative of g, are given in the table above. Our job, part B, is evaluate this integral little g of x from the lower boundary of 6 to the upper boundary of -1. Now we have a couple of things to consider here. First of all, we don't have that luxury of just being able to find geometric area because there is no graph. So we're going to have to rely on knowledge of this antiderivative of lowercase g. Now, fortunately, we were told that that is going to be uppercase g. So that's good news. Now, I know what some of you might be thinking, and you're like looking at those boundaries and you're thinking, wait a minute, those boundaries, they're all messed up, right? The lower boundary, 6, is less, or I'm sorry, greater than the upper boundary, -1. That's normally not the case. They should be switched around. Well, we're going to talk about how to deal with that later when it becomes important to deal with it. But right now, because we're not using signed areas under a curve, we can leave the boundaries like that. There's nothing wrong with integrating this lowercase g, calling it a capital G, and then just saying, all right, we're going to evaluate the boundaries in that order. So that just means you get capital G of -1, subtract capital G of 6, and then just read those values right from the chart. So that would give you capital G of -1 is +1, capital G of 6 is -2, and so the result of that would be a +1. Okay, now if you switch the boundaries and threw out that negative, it would work, but we're going to talk about that idea in a little bit. All right, I'm going to move on to quick check 3, part D at this stage, I believe. And we have a slightly different stem. The idea is still FTC, part 1, part 2, which is it? And we have the function f twice differentiable with horizontal tangents at x equal -3, -1, 2, and 6. A portion of the graph f is given above on the interval -3 to 6, and it is known that f prime of 0 is equal to 3. So for our part D here that we're going to do, we're now looking at evaluating the integration from -3 to 0 of f double prime. So if we look at that, we know that this f double prime function, which seems far removed from the information that's given, a graph of f, is probably likely going to need to be officially integrated and basically lose one of the prime marks, right? And that's exactly what's going to happen. If we integrate f double prime, we would get f single prime. And of course, our boundaries would go from 0 at the top to -3. Okay, well, if we plug in using our fundamental theorem, we have something that looks like that. Well, now we have to think about, well, where are we going to find those values from a graph of f? And the f prime of 0 at first is a little scary because we see right here is where x is 0, and we're really looking at trying to figure out what the slope of that is, and you can't assume anything about that part of the function. It's not a straight line, it's going to be curved. And we're thinking, oh my goodness, what is f prime of 0? Well, it's so often easy to overlook things that are given in the stem of the problem. And so we need to use that value of 3 here. And so we are going to do that. Now, I'm a little bit more worried here about f prime of -3 because I don't see any information there in the stem. But if I were to look at the graph and then maybe revisit the stem one more time, I see it does mention that there would be a horizontal tangent at x equal -3. Okay, and because we know that this graph is going to be differentiable throughout its closed interval, we can get by with saying that that's going to have a horizontal tangent there. So we end up with a value of 0, right? The slope of the tangent line right there would be, of course, 0, and that's our f prime of -3, which makes our answer equal to 3. Now, I skipped over C. I'm not going to do it, but you can see how C has a little bit of a different nuance with it because you're having to integrate f prime, which is, of course, going to give you f of x. So you're going to read the graph just a little bit differently to come up with its solutions. All right, so I think that takes us through the first 3 quick checks. I think I'm going to hand it over to Brian. He's going to talk about a few more of the quick checks.
Absolutely, Tony. Real quick, some of the students who were watching or teachers might have been a little bit confused on the example from 2 slides ago. I want to jump back real quick. This was quick check number 3, part B. And I think Tony wrote down, he had it written down as 1 minus -2. And then he wrote down 1, I think, on accident there instead of 3. So if you're wondering, wait a minute, why is it 1 and not 3? It was a 3. And that was my fault because originally last night when we had this table, when I made these problems, I had it as a -1 in the table. This first number was a -1. And so the answer originally was 1. And Tony had worked it all out. And then I changed it last minute on him. And I forgot to tell him I made the change. So that one's on me. I apologize, Tony.
No, I just don't know arithmetic. That's the
Yeah.
problem.
Yeah, so that was on me. Sometimes I change these problems on Tony sometimes for other reasons because it comes up later on. I had to make the numbers work out, and Tony knew the answer was 1, and I think he just wasn't looking at what he wrote down because he was basing it off of what I had done last night. So if you were confused by that, I apologize. I'll definitely take the responsibility for that one, but the answer was 3 on that one. So we're going to look at another part of the quick check today, which is going to be this idea of properties of definite integrals. And we've seen so far a lot of things like if we have area under a curve, which we're always trying to find, we can represent that as a definite integral of a function. And sometimes we have to approximate that if we don't know enough information using Riemann sums or trapezoids. Sometimes we could find the real area if the shape is geometric, not by integrating anything, but just by connecting the idea that a definite integral is equivalent to a signed area. And then we could use sometimes the fundamental theorem like Tony just showed, that we can find the area or the signed area under a curve by doing the fundamental theorem, integrating, and then using the limits to evaluate that. Well, another method would be we might not have any information really. We don't have an equation, so we can't do fundamental theorem. We don't have a table. We don't have a graph. All we have is some random information, right? And so knowing properties of integration will help us tackle problems like this. And so here we have a couple of different functions, and be careful for the lettering. So up here on the top, we've got 2 functions that are referring to the function of h, and then we also have 2 integrals involving k. And so parts A and B involve using some properties to figure out some stuff about h. And then C and D are going to be doing some things involving the function k. Well, we don't have much to go on. So this is a really good example of needing to use some properties. And these are going to come up as well during our open-ended problems. And so I kind of highlighted one important property, which says the definite integral of a function, if you flip those limits, you're going to get the same value, except it'll be the opposite answer, right? So if you flip the limits of integration, you get the opposite of what you would have gotten originally. And we're going to see that here with this problem. So I want to skip just to part C, because part C integrates a lot of different properties all into one question, but you can come back and try a couple of the other ones. So we're asked about the integral from 8 to 4 of k. And we're given some information about K here. And so some of you might be able to figure some things out in your head and to do some things, but I have a hard time trying to keep all these things straight, because we know we're going to be flipping some limits around. We have lots of negatives. And if I try to do all in my head, I end up messing up a negative sign. So what I encourage my students to do, and I might encourage you as well, is I always am a visual learner. So I always draw kind of a picture of the function K. Now, I don't need it to make it look like the graph of K. I have no idea what K looks like. But if I can get something on paper with a picture, it helps me put these pieces together and hopefully avoid some of those little mistakes on the exam by doing too much in my head. So on the exam, if you draw a picture, we're not going to check it for accuracy. We really don't even score any pictures. We realize they're there for you to help you understand the problem, right? So if we're going to look at K, I want to see if I can use some properties to figure out some stuff, right? So I have this first integral from 4 to -1 of 2 times K equals 6. And I have this other integral from -1 to 8 equals -2. So let's just pretend, for example, this is going to be -1, and then this is going to be 8. And so I know the entire area, right, from -1 to 8, the entire signed area, the definite integral from here to here combined, all of this is going to end up being a total of -2. Now I realize it doesn't make sense to call that negative when the graph is above the x-axis, right? But again, we're not trying to make this picture perfect. I'm just using it as a representation so I can put some numbers on it to see what we're doing. So I know the entire thing from -1 to 8 is equal to -2. And then I have this information right here. And so one of the properties that we're going to use is this one right here, that I do want to kind of think about this as reversing these limits. And so if I flip these limits around and write it from -1 to 4 of 2 times k of x dx, then that would be the opposite answer, right? And so in this case, instead of being 6, that piece of it would be -6. So that's one of our properties, that we can flip those limits as long as you realize it makes your answer the opposite. And then also we have this constant in there, right? This multiplier. Well, another nice property of integrals is that if you have a constant multiplier of an integral, we can bring that constant out in front and just multiply the integral of k times 2. So now I have 2 times the integral from -1 to 4 of k equals -6. And then if I divide both sides by 2, we're going to get the integral from -1 to 4 of k of x dx is going to be -3. Well, how does that help me? Well, now I know I've got this value of 4 somewhere on the graph, and I know the definite integral, or the signed area, from -1 to 4, this part right here, this has a total of -3, right? So now I know this piece on the left is -3. The entire thing would have to give me a -2. So now that will help me figure out what this missing piece is. Now I know the integral from 4 to 8, right? The remaining piece, this piece right here, well, these two have to add up to equal the total, right? The total area has to be the sum of the parts. And so if this piece is -3 and the total is -2, that's going to force this other part here from 4 to 8 to be 1. -3 plus 1 is going to give me a total of -2. And so now we look at this problem. Hey, it wants to know the integral from 8 to 4. Well, again, the limits are kind of reversed. And so if I flip these around, this is going to be the same thing as saying the negative integral of k of x from 4 to 8. And we just figured out that, didn't we? We just figured out that the integral from 4 to 8 has a total of 1. And so that means the integral from 8 to 4 is the opposite of that value, or in this case, -1. So drawing the picture and looking at the pieces is a really good way to deal with these kind of more abstract problems when you don't have a graph or a table or an equation to work with. But if you represent it and label it, it makes it a little bit more clear. So that's going to be some properties of integrals. We're going to see these come back up in the context of the other things that we're doing as well. So when we get to our free response problems, we're going to see more examples of this. I want to look at another quick idea, which is the second or maybe the first fundamental theorem, depending on which order your book teaches them in, which basically says if we integrate a function from any constant, right, a is going to be a constant and u is going to be some function of x, meaning u is a variable essentially, or an expression with a variable. So sometimes the books will write it as f of x or something like that. I probably shouldn't call it f of x because we already have an f of x in this problem. Maybe I'll call it g of x. It's just some function of x that has a variable there. It doesn't have to be x. It could be x squared. It could be sine of x, right? It could be the natural log of x. It's just something that has a variable in it. And so if we integrate a function f from a number to a expression with terms of x, that right there can be represented by some other function. There's some antiderivative of x that would give us that answer. And so the big connection I think in calculus is we can connect derivatives to integrals, right? We know they're inverses. We know that they are inverse functions of each other, but that means we can differentiate both sides of these. And so if I have capital F of x and I take its derivative, we can use the fundamental theorem, which says that's just going to be f, this original function of whatever that expression was, times u prime. We have to multiply by the u prime by the chain rule, right? So whatever expression you're plugging in to your expression here, you got to multiply by the derivative of that part right there, which is u prime. And hopefully in your class, you saw how this broke down. I'm not going to go into the proof or why this works, but it's pretty intuitive based off of the fundamental theorem that if we integrate a function, we can just take our result and take the derivative of that result. So seeing it in practice is kind of the best way to see how this works and the simplicity of it. So quick check number 5 says we've got this table of values of f, and then we have this function g. We're going to do part A. This function g is going to be defined as x squared minus the integral from 1 to 3x of f of t, right? And so part A says let's find g prime. So we have an equation. Anytime you have an equation, I don't care kind of how weird it looks, you could differentiate both sides. I think it's important that we realize differentiating is just kind of like any other function, right? If you had an equation in algebra 1, 2x minus 5 equals 10, you could add 5 to both sides, or you can add to both sides of an equation. You could divide on both sides of an equation. You could square root on both sides of an equation, right? Assuming it gives you a real answer. We could differentiate on both sides of equation the same way that we could add, subtract, multiply, divide. As long as we do it to both sides of the equation, we're going to get an equivalent or another true statement as long as we're in our domain. So if I want to find g prime, let's just treat this as an equation and differentiate both sides. And so g of x's derivative is going to be g prime. We've taken that derivative. And on the other side, we're now going to take this thing's derivative. Well, x squared's easy, right? That's just going to be 2x, no big deal. And then minus, now I have to take this thing's derivative. How do you take the derivative of a definite integral, right? How does that work? Well, that's exactly what this fundamental theorem tells us how to do it, right? It says, if you want to differentiate this, we just take the expression, right? And we can plug that right in for our variable. And so here, the derivative of the integral, those two ideas are inverses. So like the derivative and integral kind of cancel out, right? They kind of almost undo each other. So we're going to be left with f of 3x in this case. I plug it in. Then I have to multiply by the derivative of what we plugged in, right? Remember, we have to multiply by the chain rule, which is by u prime. And so since we plugged in a 3x, we're going to multiply our answer by 3. I think one common mistake that students do is they forget the chain rule, they forget that multiplying, or what they'll do is they'll look inside of these parentheses here on their answer and think they have to multiply by the derivative of the parentheses. And that's not what we're doing, right? You got to make sure that what you're multiplying by is the derivative of the upper bound here, or the lower bound, wherever the variable would be. It just so happens that when I plugged it in, we still got a 3x in the parentheses. So it kind of worked out the same, but really make sure that you're multiplying by the derivative of the upper limit, which would be 3 in this case. And so now that we have this, we can figure out what g prime of 2 is. And g prime of 2 just means plug in 2 for all of our values. So 2 times 2 is going to be 4, minus f. If I plug in 2 here, it becomes f of 6. times 3. And all of a sudden, this table of values up here starts to make more sense, because if I want to find f of 6, I can look right at the table. That's a minus sign, not a subtraction sign. F of 6 is going to be 0. That worked out nice, didn't it? 4 times 0 times 3 is just going to be 4. So we get 4 for that one. We're not going to do part B, but I want to illustrate what I mean by why we're multiplying by the derivative of the limit and not what's in parentheses. Because on this example, when it says find h prime of x, well, first of all, our limits are expressions in the bottom limit, right? So one thing we could do is remember, we can use our properties of integrals that we just talked about, and we can flip those limits, couldn't we? And we can write that as cosine of t squared minus 1 with a negative sign in front. So now when I go to plug that limit in, we're going to have a negative in front of our answer. And when I go to plug it in, it's going to be cosine. And then if I plug in the natural log of x for the variable here, it's going to become the natural log of x, the whole thing squared, right, minus 1. That's what we would get. We plug that in. And we know we have to multiply by the chain rule, right? That u prime. Well, this is what I mean by saying, don't look here. We're not multiplying by the derivative of this. We're always multiplying by the derivative of what that boundary was, right? So you're multiplying by the natural log of x's derivative, and natural log of x becomes 1 over x, right? So that's what I meant by saying make sure you look at this piece and not what's in the parentheses, because sometimes what your upper boundary is and what you get in your result aren't going to be the same thing. So there's another quick check on here. There's a lot of extra good problems that you can look at. I want to push past quick check number 6, this accumulation model, because we're going to see it on one of the FRQs here in a second. So we'll leave these for you to try. And then I want to jump over back to Tony so we can get at least a glimpse of a couple of free response problems that will take these ideas, put them into practice with other ideas, as well as connecting it to some other AB topics and some BC topics, so you can get a better feel for how these things might all appear together on a free response problem this year.
Certainly, I think what I will do here, I'm going to skip ahead. And after all, this is AP Calculus BC Live. So why don't we jump into a BC question? So if you're kind of flipping through, following along with the document, I'm going to go to BC1, Part N as in Newton. And I know you might be looking through that problem, or at least looking at the slide and saying part N. Well, that's not where it ends. It has a few more parts. It goes up to part P, but that's not a surprise. It's called the Fundamental Theorem of Calculus for a reason. It's very fundamental. It permeates through so much of calculus. By the time you get to say around the second semester of an AB course, the more calculus that you would take after that, you're not going to shake this idea of the fundamental theorem. It's going to pop up in almost everything that you do. So in this true BC question, we have this graph of f prime of x, and the function f is continuous and differentiable for all x, and a portion of the graph of f prime, the derivative of f, is shown above, and the interval for which we see it is from -3 to 6. We know that f of 2 is -3. That might come into play on some of the problems. We are asked to evaluate the definite integral from 1 to 3 of sine of x times f prime of x. Now, I may have given this away by saying it was a true BC topic, so you have to think about what kind of integration technique that you would want to employ. But seeing as how you see the product of two functions, one of which is what we call transcendental, that just kind of means weird, right? Those are the weird functions: trig, inverse trig, e to the x, natural log. It's very likely that the only choice that you might have to integrate is to use integration by parts. But you have this elusive f prime of x that's going to be problematic. And that's going to play a very big role in deciding what do you want to let your u equal and what do you want to let your dv equal. So if you kind of sit back a little bit and think about this, f prime of x, how elusive is that, especially on the interval 1 to 3? If we were to look at this graph at 1 and 3, we should notice that the f prime is just nothing more than that line segment. So you are not going to have such an elusive f prime after all. You are going to be able to find the equation of that. And I think that's it's going to be a necessity in order to solve this problem. So a couple of different ways you can do that. You can just use the simple idea of a couple of points, 3, 2, 1, -2, and we can find the slope fairly easily. Let's say if I take the difference of the y's, I would have 4 over the difference of the x's, which is 2. So our slope is, of course, 2. Pick one of the 2 points. I'll choose this guy here, and we can use our point slope formula very nicely. And let's go ahead and solve this completely for the y. And we would have 2x minus 4. And really what this y is, it is the function f prime of x equation. Well, at least for a little bit, right? It's valid on the interval 1 to 3 at least. And so that's what we're going to use. We're going to place that 2x minus 4 in for that f prime of x. And now once we've done that, we can make our decision about what our u and dv are going to be. Again, students and teachers set this up a variety of different ways. The table method will still work here as long as you're clever and you want to use the algebraic piece for the u. I know there's lots of mnemonics out there like liate and liate and so forth that can help you dictate what you want your u to be, but just make sure that you choose the algebraic piece here, because our goal would be ultimately to have this disappear, right, into nothing, right? Take as many derivatives as you need to cause that to become 0. Now for the dv, be very careful here because we have to integrate going upward to get our v, and the antiderivative of sine is a negative cosine. And now we just assemble our integration result, u times v. And notice what I'm doing here. I'm going to write my u times v. Maybe I'll put my negative sign out to the front. And then I'll subtract the integration of v times du. Well, in this case, I see that I'm going to have a 2 times negative cosine. So I tell you what, I'm going to go ahead and change that to a plus and just pop my 2 out in front and kind of simplify it on the fly. Now you'll notice that, oh my goodness, blasphemous. I'm not putting in any of my my boundaries of integration. Well, that's okay. I'm going to erase this equal sign so that I don't run the risk of trying to assume that I'm linking this back to this, because those would not be equivalent to each other. But I'm just going to sort of work this off to the side as an indefinite integral. And then once I'm finished with that, I'm more than welcome. I'm certainly able to reintroduce those boundaries, and then I've essentially reset the problem. I know there are a lot of teachers out there that are like, no, we don't want to do that. We don't want to do that. I have found, and trust me, I teach a lot of students. We have 300 students at my school taking calculus, and I find that so many of them really get lost trying to put those boundaries into an expression that has been integrated and then into an expression that has yet to be integrated. And so I find that they have more success by just working it out without the boundaries. But I re-emphasize over and over again, make sure that you plug them back in. One of the best ways to do that is to circle them in the original problem so that your attention is drawn to them. So to finish this up, we can then see that this guy's not going anywhere. We're just going to let him kind of stay where he is, and then we're going to integrate the 2 cosine, which is 2 sine of x. Now we can just go ahead and reintroduce those boundaries of integration. That's called our restart. And then when we plug our 3 and our 1 back in, I don't think we get something that's necessarily pretty per se, but that's okay. It's going to be written in terms of cosines and sines, but it would look something like this. Just want to be really careful with the usage of your parentheses here, because I need to subtract, and now I'm going to plug in my 1. 2 minus 4 is -2, and I know this looks pretty awful, right? There's a lot that can be done with it as far as ruling out some double negatives and whatnot, but I'm just going to leave it like that and let you clean it up. But it's not going to get much better. We don't know the cosine of 3, the sine of 1, et cetera, et cetera. So there's a nice little BC problem that kind of connects this idea of FTC. Brian, what do you got here with BC2?
Sure. Thanks, Tony. So we're going to fast forward to BC2, and I hope that you download these files because there's like 16 parts to BC1, and Tony just got through one of them because of our timing today. But there were 15 other parts that give you a really good collection of problems that will take you through a whole bunch of A/B topics, plus some more integration things that we talked about at the beginning of the lesson, plus more BC ideas, kind of like the one that Tony just did just now. So BC2 also has many, many parts. I think maybe only 6 or 7, so it's a lot less. But I want to highlight one or two really quickly before we finish up, because we haven't talked about this much. But part A on BC2 talks about this average value of a function f, right? This idea of how do you find the average value of something? That's an important idea. We know they've taken that out of the AB exam this year. It's normally an AB topic. They've taken it out because it's part of that unit 8 that won't be tested, but it will be on the BC exam potentially. So we're keeping it. And we haven't mentioned it yet, so we wanted to make sure we at least did one problem today that introduces this idea. And so you might remember the average value of a function is given by this formula that I put here in the box, right? The average value of f over an interval is going to be 1 over b minus a times the integral from a to b of f of x, right? So you have to be careful that when you see the word average, sometimes we're asking for average value, which is this. Sometimes we're asking for average rate of change or average rate, which is very different, right? That would be the slope of a secant line on the graph. And so in this case, to find the average value, we're going to integrate f, but we don't have an equation for f. That's why it says approximate it using a trapezoidal sum, right? So we're going to tie this back into the very beginning. Tony did a really good example of a Riemann sum. We could also be asked to use trapezoids. And so to refresh your memory, the area of a trapezoid is 1/2 h times base 1 plus base 2. And we're not going to finish this problem out, but I want to get it set up because I want to point out where common mistakes would be on the exam. And so whenever you want to find the average value, it's really helpful to write that formula out first, because what students do is they see trapezoidal sum and they just start going right into trapezoidal sums and they don't write out what they're doing first. So they either forget the average part in front, or at the end of the problem, they realize, oh, shoot, I should have found the average value. I have to divide my answer by something. And they end up just dividing by something. And they have these equal signs throughout the problem saying these things are all equal to each other. And they divide by something at the end. And they still use an equal sign. And now they have that linkage error where they have this approximation and they said it equals the same thing but divided by 4. So we want to be careful how you do notation. So setting up the problem is always helpful before you start jumping in, plugging in numbers and doing it. So I would recommend when it says find the average value of f over the interval from 0 to 4 to realize, oh, that's just going to be 1 over 4, right? B minus a, 4 minus 0 is 4, times the integral from 0 to 4 of f of x dx. If I want to find the average value, I have to come up with this answer right here, 1/4 times the integral. So then I realized, well, I can't integrate f, right? I don't have big F in the table, so I can't use the fundamental theorem like we might want to. However, that's why it says to approximate it using a trapezoidal sum, because we can approximate the integral, right? Remember, when you do a Riemann sum or a trapezoidal sum, what you're approximating is just the definite integral part. That's the piece that you're approximating. So the trapezoid will take care of the part in red, but then we have to make sure we have that 1/4 as well. So this average value is going to be approximately equal, like Tony mentioned, we're approximating it. Don't forget we have that 1/4 in front, right? That's the part that students forget, and they end up just dividing their answer by 4. And depending on how you use equal signs, that can be a little bit dangerous of saying a false statement, even though your answer is the right number. So we have a 1/4 in front, and then we want to approximate the integral using trapezoids. And so remember, our trapezoidal formula is going to be 1/2 the height of the trapezoids times base 1 and base 2. And I mentioned in the last example, I'm a big picture guy. I like to draw pictures to help me understand. So whenever I want to do something like a Riemann or a trapezoid, if we're trying to integrate f by approximating, I draw that generic curve. It's kind of a picture of f. I don't try to make it match the table. I'm not trying to match the numbers and the heights. I just draw the same curve every time, and I label it f. And then I can label the x values along the bottom. We have 0, 1, 2, 4. You'll notice they're not evenly spaced. There's not proper, like I know that the scale is off. And then I label the heights of each one. So according to our table, the heights would be 6, 2, -1, 0. And I label those next to those vertical lines. And I do that and I realize, okay, it doesn't make any sense that this would be a height of 0, right? Because this is obviously, if it was a height of 0, it'd be on the x-axis. This isn't a -1, that would be below. But we're not trying to make the picture the correct representation. I'm only drawing this so I don't make any mistakes when I pull my numbers into my Riemann sum or into my my trapezoidal approximation. And so we can see we have 3 regions automatically. That's why it says with 3 subintervals. And then for each one of those, we're just going to use our area of a trapezoid. And every trapezoid has this 1/2 in front. So I can go ahead and put the 1/2 out in front. And I don't have to write it each time. What I could do is just put a 1/2 and then do my h times base 1 plus base 2. And so if this is my trapezoids here, remember this piece right here is our height. So from 0 to 1, the height is just 1. And these vertical pieces are going to be your 2 bases. And so when I have the picture there, it's really easy to make sure I don't mess up the numbers or pick the wrong numbers. And so for the first space, the height is just going to be 1. It's this piece right here. And then our 2 bases are those parallel sides, which are vertical in this case, which would be 6 plus 2. That's going to be our first trapezoid. And then our second trapezoid is this little region right here. This one also has a height of 1 from 1 to 2. So we're going to have a 1 there. And then our 2 bases are going to be 2 and -1. And then finally, our last trapezoid is this little piece right here, which is going to be a height of 2 from 2 to 4. And then our 2 bases are going to be -1 plus 0. And if I put my big parenthesis around that, and then my big bracket around that, now I have my whole answer. Of course, we don't have to reduce or simplify because we have a numerical answer. But the key is going to be, don't forget that 1/2. And if you do forget it, don't just divide your answer by 1/4. I mean, not 1/2. Don't just divide by 4. You might want to make sure that you don't have any equal sign linkage errors. Tony, in the last example, did a really nice job of making sure, like, if we're going to do some side work, don't use the equal signs. Do it and then bring it back when you're done. So equal signs are going to be a big deal on the exam, because if you say something's equal, we're going to hold you accountable for that. So that was a nice little average value problem that we haven't seen before. I would encourage you to go through these problems, because toward the end of question 2, we have a really kind of cool connection to some series problems, right? That unit 10 is those series tests that we did, geometric and p-series. There's a couple of really nice problems in there, which is why this table has these functions a and b. You might have been like, why is there an a and a b in there? Well, we're going to tie these values back into some series ideas. And so you're going to see a good example of a p-series problem, and then a nice tie into some geometric series. You'll also see on both BC1 and BC2 some reminders on doing arc length, reminders on Euler's method, some good Taylor polynomials, all kinds of different things in the BC topics. So try those, because that's going to give you an idea of how all these things might be intertwined on this year's exam. The real exam, each question is not going to be as long as these two, right? This is much longer than the real exam would be. So don't think, oh, this should be a 25-minute problem. It might take much longer than that, but it's giving you all kinds of possibilities of what might be a valid question for this year's test. So with that said, try those out. This is really good practice for the exam. I hope that you'll enjoy those. And then our friend Ted Gott, as always, will have the solutions posted on Dropbox tonight. And then if you're a teacher, the AP Calculus Facebook group, he posts those around midday once he gets the keys done for that day. So teachers have access to them a little bit earlier than the students would. And so, as always, we're going to end our session with some tweets with Tony, followed by some good news and announcement Tony is going to share out, and our dog of the day.
All right, so we want to keep these tweets coming in. They're starting to get a little bit thin. We're kind of having to scrape and find some of these, so we want to encourage you to use the hashtag #APTeachersRock. And for the teacher side, we're going to give a shout out to my BC teacher, Ms. Hansberry from Little Rock Central High School. She worked so hard to prepare us for the AP exam and teach us wonderful calculus. So a shout out to that wonderful teacher from the great state of Arkansas. And as far as our AP Students Rock, we're really wanting to try to get more of these in. We know that there are fewer teachers out there that are watching, so it's a little bit more of a challenge for you guys to call out your students, but we certainly encourage them, because we're starting to run a little low on these. So for our AP Students Rock, I want to give a shout out to all my AP Calculus BC students. They are all studying and working together to prepare for the examinations despite the challenges. And I know who sent this. It's a wonderful teacher by the name of Mr. Casimir Uchegby from Lakeview Tech, just outside of Kenosha, Wisconsin. I had the the privilege of working with Casimir in a training just not too long ago. As always, if you're having trouble, we want you to make sure that you reach out to the College Board at cb.org/tech. And as far as what's ahead, we have a couple of more connecting AB to BC with particle motion and area and volume, and we're going to move into our problem types next week. But we'll go into a little bit more detail about the final week, where Brian and I are going to have a wonderful opportunity to get you guys really ready for this year's AP exam by walking you through and having you try a few timed questions under a little bit more of testing conditions. So I think the only thing left, we're going to recognize a couple of our little doggies, right? The dog of the day, that's Kona and Cody. And how appropriate for Kona and Cody to make an appearance from Galesville, Maryland, because those are the two wonderful dogs that belong to Mr. Ted Gott. He is the third wheel in this wonderful AP Calculus BC machine, and we appreciate Ted, and we want to definitely recognize Kona and Cody. So with that, Brian, great show. I can't wait to get back on with you tomorrow, and we're going to have Anthony G take us out. We want you to stay safe, stay healthy, and keep learning, everybody.
See you guys.
AP Calc, yes, AP Calc. Welcome you to AP Calc, yes, AP